Czy pan profesor jest gotów do prezentacji?
Tak, jestem.
To ja oddaję głos panu profesorowi. So, you're welcome.
So, thank you very much for the invitation. Yes, so somehow a little bit aphoristically can speak predicting the unpredictable, right? So how to forecast the future. And I like this Niels Bohr phrase, it's hard to predict, especially the future. But the question is, what is actually predictions? Most people think, I mean, predicting epidemics means extending the figures which we have here to the right side, right? So this is different countries just to autumn, beginning of autumn last year. And you would like to know how that goes on. And that is actually a pretty difficult task. But it's not the only task. And already the first mathematical model, Franek mentioned already that we have more than 100 years of epidemic modeling, which was done for malaria by Ross and Lotka independently in the beginning of the last century. It was not the task of predicting the malaria, but what is the most effective way to control malaria? So what you should do that the numbers go down, or eventually you don't have any malaria anymore. And the reality is relatively complicated. As you can see here, the biology of the malaria, it's a little bit more complicated even than the COVID dynamics. So this was a different question, just predicting how it's going on. And I would somehow say there are four major groups of or categories what prediction could mean. And of course, the forecasting long and short and medium time predictions like weather prediction, it's still a challenge and it's difficult to do. The other thing is more on what is the effect if you want to do something. So the analysis of the efficiency or the effect of certain countermeasures. So in infectious diseases is how many contacts you have to reduce to achieve a certain target, how many people you have to test and quarantine, how fast it can go on. We have contact tracing, all these NPEs, non-pharmaceutical interventions, have a different efficiency depending on how they provide it. And they, of course, interplay then with the medical parameters and have a certain epidemic outcome. And to understanding these dependencies, I think, is an equally important, if not even the more important part of an epidemic, of a prediction. The third group is, I think, a very important thing as well, understanding structural effects and the impact on the epidemic. So we focused here very much, for instance, in theoretical studies on households. I will say a few words about this, but also regional effects or mobility. People don't work at the same place where they live, which in great detail is reflected in Franek's model, is an important structural a feature of a given country, and it may impact the epidemic. I think is an important part of mathematical analysis, and that's something you can actually only do with this kind of modeling. A third group of things would be predictions on what will be the patient outcome if a person is infected. And our colleague from Warsaw, Przemysław Biecek, has actually used machine learning methods and from artificial intelligence to make predictions models for patient's outcome as a function of different features the patient has, the age, the gender, the comorbidities, and so on. So this is a different group of predictions. It's also used mathematical models, but very different ones. So here is an example for predictions for, I think it's Germany. We have since more than a year a so-called German-Polish forecast hub, which is now transferred into a European forecast hub. Franek is submitting forecasts there. We doing is. And we don't do it only for Poland, but it's for many countries available here. And you see the difficulties which people have even with relatively short-term forecasting. So up to 4 weeks, the predictions here are only done. that there is a tendency when the cases are rising, you have an overshooting of the predictions. So you see the black line is the real numbers, and the points here are always then attached to the 4-week predictions, and the columns are the confidential bounds, the intervals. They become relatively huge, and at the beginning of a wave you have usually an under prediction, so you come a little bit sometimes too late, and then when you decline, then it gets most of them get them correct here. For Poland, for US, it's 40 teams predicting. In Poland, it's I think about 15 teams which do predictions for Poland and Germany. And there are very different types of models. Franek mentioned already a few, and I will say a few lines at the end. There's also some purely statistical model, timeline analysis and predictions, or a baseline model to which all the other models have to compare. If you say, like, the weather stays as it is today, so the numbers stay the same, right? This is somehow a statistical naive prediction, but it's not always even easy if you don't do it right to be better than that basic prediction, right? So in weather forecasting, for instance, if you say that the weather forecast, the weather is tomorrow as it is today, you have a 70% success rate. And with advanced modelings, we're coming up now to 85–90%. So looks just a little bit, but it's pretty hard actually to make good predictions. So here's the MOCOS predictions for deaths and cases for the second and the third wave here. The green barrows are our predictions. We see we also had a tendency to overshoot, especially in terms of the deaths here in the second wave. I think we have a large undercount of deaths, especially last year. We also have it in the fourth wave. And in the cases we have done a little bit better, but in overall I'm quite satisfied, and we definitely are in the upper group of models. And I don't have a picture with Franek's recent predictions, but I know that ECM, especially after they updated the population, has excellent predictions in the for Poland here in this comparison in the forecast hub. Right, there is still an interesting mean model prediction. So it's an ensemble which takes the average of all the models into account. That is the green barrels here. And you can go on the page and you find a lot of additional information here and all the types of models, and also with a short description of the models. Franek mentioned already the main groups of models. We have a classical ordinary differential equation system compartment model. You can extend them also into partial differential equation model. And then we have the large group of agent-based model. Depends a little bit on the disease you want to describe which one is the better tool or the more appropriate tool. And the aim of all is, of course, uncovering conditions for outbreak, how to control the spread, and how to predict incidences. And this is the kind of basic example of such a compartment model. You have this susceptible infected removal groups, the deaths, and say the people which have a certain immunity here, or the quarantined people. And it's relatively easy to write these models down, and also relatively easy to analyze them numerically, but also analytically. So the epidemic classifies things into, according to this major group: susceptible, infected, removals. So there are things where are no removals, right? Mushroom infections, for instance, or herpes. You can get immediately also again infected. Then you have an SIS epidemics. So after infection, you can immediately get again infected. We are here more in the SIRS class. So after a certain time, you have immunity. Franek mentioned already, we can get reinfections. And that is somehow the most complicated class. So in the medical literature, Ofman and E is added here, which meaning there is a phase after infection in which you are not yet infectious, but essentially it's just a technical additional subgroup which you add here. This is the evolution of the malaria model, and the evolution of these models in the classical sense. Compartment model is usually by adding new compartments, right? You add another compartment which you think is relevant, and you see it's an ongoing thing, and you can spend your whole life in adding compartments for malaria and discussing the effect of those things. They all originate from the basic model. So the pluses and minuses, I think one should mention here also, ODE models are easy to describe. That's why the majority of the publications are on ODE models. They are easy to simulate, they are relatively easy to analyze, but it's difficult to add heterogeneity in. Right? Household sizes, regional aspects, schools, workplaces, all the stuff which agent-based models have not great difficulties to build it in. It's just the data quality very often which has to be, is the problem here. Are difficult actually to do in ODE. And if you have an ODE which eventually 2,000 equations, then it's also not so convenient to work with it anymore. The agent-based models, actually the pluses of the one are the minuses of the other one, so it's easy to add the heterogeneities. The problem is you have many parameters, so in the fitting you could have a problem. It's much more difficult to analyze. Some people even think it's impossible, which I doubt. I think we have here done also a lot of activities in analyzing things, and it's computationally expensive. Right, so that is why the agent-based model, even if I think they are in many aspects superior because they describe reality better, are not forming the majority, and large agent-based models on the European scales are not so many. Great Britain has one, Austria has one, Germany has none at the moment. They have a large project now, a call, and they got 3 million for building up a model. Franek and me, we are also as advisors here involved, but Poland has two. In terms of modeling, I think on a pretty good side. Yeah, so one key parameter is the reproduction number. I will just briefly tell it because our model directly builds up on individual reproduction numbers, and I will speak on a couple of aspects of this reproduction numbers. This is loosely speaking, it's the mean number of secondary cases a typical infected generates. And the classical wisdom is if this number is larger one, the numbers go up. And if the number is less than one, you have vanishing epidemics and it dies out. And if you are at one, then you are at a critical state. Somehow numbers will not really go down. They will also not go up. And there is a deep reason why this is actually more or less correct, these pictures. So agent-based model are individual-based, so you represent usually the whole population, as Franek already said, and with agents or individuals which have individual properties. And everything depends on this individual's properties, right? So the contact structure in especially, but also the progression of the disease. And on top of this, you have a time depending change of the environment, and you have targeted complex countermeasures. So, but everything works actually on a network of contacts, right? Infection, at least the type of infection we have in COVID, is transported via a more or less direct close contact between people. So you have to understand the structure of contacts and on which it depends. Spatial aspect is one thing, but age is another one, and the household is another one, and the workplace is another one, and the school is another one. And then you can go to what we call its essential thing in our model or approach also to what I call the infection graph. The infection graph is a graph which only represents potentially infectious contacts. So it's a sparser graph than the real contact of between people, right? So you draw an edge if somebody was or is in close proximity of another person. but not every contact provides transport-related infection. So the infection graph takes only care of the really infectious links. And in a certain sense, you test for every person, if he would infect it at a given time, who he would infect. And that is a random thing, right? A random sampling of secondary cases you produce out of the population, depending on the features of the individual, and everything might be also time dependent, actually is. And then you get a time dependent network of eventually infectious contacts if one person would be infected and the other one would be susceptible. That is the basic network structure on which somehow conceptually our models rely. And I would like to think in terms of this kind of infection graph, right? The real epidemics is then a spanning tree among this infection subgraph of the real contact graph. And pioneers in studying, and actually when I mentioned before that at secondary numbers less than one, larger one, there is a big difference because it distinguishes whether the epidemic goes down or up. But there is a deep structural change in the network structure behind this. And the first people who actually revealed it was the Hungarian mathematicians Paul Erdős and Alfred Rényi, which discovered in a very simple model of contacts or a network of things on which you can propagate an infection, a remarkable thing. So the model they had in mind was very simple. It's a so-called Erdős-Rényi random graph. With a certain probability between two random people, you have a contact, and this contact probability is tuned in such a way that the mean contact per individuals is a fixed number. And let's call this mean number of contacts you have R. So it will actually be turning out that this will be the reproduction number. So it's described a connectivity, but I'm looking now only of infectious contact. And they figured out if the structure, the connectivity structure of a graph, of a random graph, changes drastically when you jump from values less than mean number of contacts 1 to mean number of contacts larger than 1. And essentially depends not very much on the distribution we have. Below this mean number of friends or contacts or people you would infect 1, you have a breakdown of the connectivity of the network in small isolated components, all of logarithmic size. And as soon as you go above 1, you have one large connected component and then a few isolated spots. And everybody in this connected component would actually get infected if an initial infection would start within such in this component. Here I have a numerical example given. You see on the left side reproduction number 0.9. The infection graph splits into small components. All of them are small. As soon as you go above 1, a large connected subgroup of nodes appears, and spreading, if any node gets infected, you start an infection with any node inside here, everybody in this connected component will get infected. And if you go with R equal a little bit up, very quickly, a large part coming close to 90 or 100% of the nodes will get infected. So there is a phase transition, a deep phase transition behind what's happening between reproduction number less than 1 and larger than. The graphs Erdős-Rényi used here are very simplistic, and they don't have any features of the individuals, but there are extensions of this. And that is actually there is a class of graphs which we build our model in, which are defined via so-called contact kernels. So individuals have features. A feature vector is assigned to the individual, which can include the localization, whether he is working or not, how old he is, and where he lives. And but not only those features, but for instance, also the feature how long he will be infectious, and how long it takes from eventually infection till he becomes infectious. So these are features, or whether he will discover in the process of testing. These are features you can add a priori to the feature vector of individuals. And then based on these features, you define the probability of a contact. That means an infection taking place between individual I and J, if say individual I would be infected. Depends on the features of these two nodes. And that defines then a transmission probability, and then you get an epidemic dynamics. And the class of graphs in which this is mathematically embedded was mainly studied by Bolobas, Janssen, Riordan in 2005. They wrote a big paper on that and derived many very interesting mathematical results on that. And you see on the right side what I mean by heterogeneity here, right? So a typical feature agent-based model have, but I just wanted to mention you can do mathematics still, even with very large complex heterogeneity in the population. And it's actually also helpful when you want to build up the model perspective, right? So what we assign, for instance, in our MOCOS model as feature vectors is, of course, age, gender, work status, household sizes, but also incubation time being infectious outside the household, whether people are tested or not tested, whether people will be quarantined, the hospital stay. This can be a priori assigned if a person would get infected with a certain variant, including its vaccination status, whether he goes to a hospital or not, whether he dies or not. These are all things you can gamble out in advance and attribute it to the individuals. Contact tracing is more complicated. This you cannot immediately put here in, but I will not speak about this. Now, so there's one technical difference between the agent-based model of ECM, Dr. Franek's model, and our model, is a little bit the perspective how we view the dynamics of the epidemics, which can be equivalent presentations, but in the realization, it's a little bit a technical difference. We look somehow from the perspective of a freshly infected person, and we decide then who he will infect, in which age group, and where. And in Franek's model, it's more from, if Franek correct me if I'm wrong, but it's more from the perspective of the non-infected. He looks around and he sees who is infected in my neighborhood. And depending on the people infected in my neighborhood, I have a certain probability to get infected. And then you update the system.
That is exactly how you said. And this is, for me, amazing that we are starting from two different, sites, from two different ends.
Right.
But yeah.
Of course, they are exchangeable. I mean, you can both models can be formulated either way around. But it's in the programming, of course, you go a different path of the things. All right. So we have an event-driven in continuous time here. So all infection events happen at different times, and we update one event will have then an impact on the following event. And we have also a synthetic, I will not speak here as much as Franek about the synthetic population. Then have the new population in the ECM model contains more features and has, especially in the regional aspect, but also workplace or school, a finer resolution than we have here. But we also have a whole population of Poland here based on census data and available data from GUS, etc. We plan also to come up with a regional model in the next future, but that depends also a little bit on the workload on other things, and let's see. And we have, of course, a realistic household structure, a realistic age distribution, and very much put focus also on representing correctly social intervention measures as contact tracing, contact reductions, and things like that. So, this is the input parameters. I will not speak about the technical things here. I skipped this over a little bit. But I would mention, so we have different kernels here, these contact kernels for different aspects. So as a household interaction, there is a sporadic interaction, so corresponding to public transport usage. There is a friendship kernel and there is a hospital kernel. and everything is age dependent. And the geographic part is the thing we haven't yet really incorporated here. In terms of the algorithmic flow, as I already said, when a new person gets infected, we sample, depending on its features, its individual reproduction number. So how many people he will eventually infect. But first, we don't look whether these people are yet vaccinated or not. And this is then sampled. This R value is taken as the mean value of a Poisson distribution, and with Poisson distribution, we sample the number. And then we look whether the person can get infected he has chosen, whether it was a contact, for instance, who was protected by immunity because he was vaccinated, or he had immunity because he previously was infected. And then we decide when the person actually gets infected. So there is maybe a week or 10 days behind this decision who you infect and when the person really becomes in real time infected. And at this real time moment, you check again whether the person was not put under quarantine because, for instance, his household went under quarantine, and then of course the contact could not happen. So there is a two-stage somehow process here to generate the newly infected, and the kernels define what features the newly infected individuals which were infected by a given individual happen, and with every new infection you update the system, right? So it's conditional Poisson distribution which dominate here on the side of mathematical distributions. This is technical stuff I don't want to speak about. Now, one of the outputs I like very much, Fredrik showed already such a picture here, are heat maps, which somehow scan parts of the parameter space and see how certain important observables, like the total prevalence, the number of cases in the maximum, the number of the time till the maximum, if you inject infection now in the population, how this depend on the parameters. And I think it's you can get a lot of insights here. And they are relatively independent of the actually development. I mean, they are really just structurally dependencies of your model on certain parameters. So what I here have, for instance, represented, this was, I think, for the British variant, the alpha variant simulations, is the dependence on the prevalence. How many people would get infected in a susceptible population as a function of reduction of contacts and efficiency of contact tracing. So you see efficiency of contact tracing. If it's high, it can buy you a lot. For Omicron or Delta, unfortunately, this efficiency must be extremely high to really stop in epidemics. But we see in some countries which have extremely efficient contact tracing, like Asian countries, that you can essentially control an epidemics by that. Not with the technical tools and the political will we have in Europe, but in our countries, it's really an efficient tool. Next to a little bit contact reduction still is needed. There are some other heat maps, and I want to show you already a heat map here for the Omicron, but which is contact reduction versus level of. So on the right side, it's not level of vaccination, it's really the effective immunity in the population. So 0.5 means half of the population is immune. They will not get infected if they are exposed to the infection. And F is the contact reduction here. And what you see, we are in Poland at the moment, maybe with terms of the contact reduction at 0.4, 0.45 at most, which is coming by behavior of people and masks wearing and a few rules which we have in action concerning infections inside workplaces, for instance, and so on. I mean, it's not that we have, has no protection at all, no care. But you see, with the level of immunity we have right now, which is a little bit less than 1/2 with the Omicron, we are in the middle of the green part, which essentially means everybody who can get infected will get infected. And to come to a better scale, it stays green actually very long, even if you would add much, much stronger restrictions. Only if you come close to the phase transition, you would really, which means the epidemics would be stopped, you get down to smaller levels. So it's extremely hard to stop the Omicron wave by contact reduction at the level of immunity we have right now in Poland. So I see very little chances. A little bit better looks it if you look at the time till the peak. So we are again here at the border between the blue and the green region, so a little bit more in the blue, which means we have something like 60 days, so 2 months, from an assumed initial number of 100 cases, right? So this is the setup here. It's a little bit simplifying setup. So if we had these cases at the beginning of December, which is maybe not an unlikely situation, we would now by end of January or beginning of March see already the peak of the epidemics, right? It might be a week later on, depending on where we exactly are. But here you see if you put in restrictions, you gain something, right? So even if you are still far away from the epidemic threshold, you can a little bit slow down and shift the peak to the future. So I think it would be still recommended from my perspective to do something. In terms of the maximal numbers, this red is everything here goes up about 200,000 cases per day, true cases. They go actually much higher up. And I know that's also in Franek's model the case. And again, you would have to come very close to the phase transition to have a really smaller number, right? Which I think is very difficult to achieve. Now, I maybe have still a few minutes to say something on households. I don't want to go into the mathematical theory here, but just mention a few things on the impact of household as an important structural risk factor, and especially now back with Omicron. So households group people into groups, of course, and the main point why households are important is that all these restrictions, whether mask wearing or whether we would impose some contact restriction, they don't work in households, right? The households contacts stay the same, whatever the outside is going on. And the connectivity structure between households is a different one than the connectivity between people in terms of their contact structure, because in a household of size 3 and a household of size 4, by purely combinatorial reasons, has a 3 times 4 increased probability that there is a contact between them. The probability is small, but compared to two single households, the likelihood that there is a contact goes with the product of the household sizes. And that changes the network structure if you look at the network as a network between households, and households infect other households. So there is still the household attack rate, which I denote here by H, by a little a. And with some simplifying assumptions, you can do some mathematics here and come up with a household reproduction number. And this is on the right side. This is the mean number of households which get infected by a typical infected household. And I will explain what the numbers in this formula are. C is the mean reproduction number outside the household. So a typical infected will infect C cases outside the household. That depends on countermeasures, restrictions, whether you put people in quarantine or not. It depends on many things, and it's individually fluctuating. But actually, the relevant thing is only the mean value here. Little AH is the attack rate in the household, which is for delta about 0.2. And M2 is the mean squared household size. And the square comes here in because, as I mentioned before, the probability of contacts between households goes as a product. And then you have to do a couple of mathematical things that you end up really with this mean squared household size. Now you given household number, and why you have to divide here at some point is because the number of household in the household graph is not the same as number of individuals, right? If the mean number of household is capital E, then in a country with n individuals, you have n divided by the mean household number households. So to scale, to get the proper scaling, you have eventually divide by the mean number, and this comes out at the end that the reproduction number of households comes with this quotient, and this is a boost factor. So if the mean square number divided by E is large, you see you have an acceleration on the out household contact structure by the household impact. And what I plotted here is now an interesting, and of course you could do this also and even better with a real epidemic agent-based model and looking for the different countries. The problem is we don't have population structures on the level that Franek has, but even on our population structure level for our European countries. It would be a very challenging task to generate this. Then you could study and compare the different countries and see what is the difference. If the everything else is the same, what is the difference then in the outcome of the epidemic? So what we did here is a little bit a simplification. We used only the household size structure, so which is known, and this is plotted here, it's this moment ratio. And for each country, we estimated here very roughly at the end of the third wave, not taking into account at the moment the different age structures, the number of infected population accumulated by taking all the deaths, including the excess deaths, and assuming that we have an infection fatality rate of 1%. It's a very simplistic thing here. In reality, is a little bit more complicated, but the rough picture is still okay. And so that gives you the prevalence more or less by end of May, before the vaccination really impacted the epidemics very much. Poland is a little bit underestimated. In reality, we were closer to 0.4 because we had a younger population. But we do the same mistake somehow for all the countries here. And then you can compute, and that is somehow interesting, you can compute, once you know the M2 and the E, how large the mean C value, the mean reproduction number, had to be to achieve this level of prevalence in the different countries. And the blue dots is the predicted prevalence if everybody would do the same as the mean average Europe did, right? So there is, you can look at Europe as a whole, as one country or as one big town, and estimate what is for all the infected in Europe, the mean out household reproduction number, which would give you, with this household size distribution you have for the whole of Europe, this prevalence. And these are the blue dots. And if a red value, which corresponds to the prevalence based on the death statistic, is much below the blue one, you did a little bit better than the mean in terms of restrictions and NPEs. And if you're above, you did a little bit less good than the mean. And we see, of course, some countries, the Norwegian countries, the northern countries, did all a little bit better. But many countries like Germany, Sweden, France, Great Britain, Spain, their difference is not because they did much more or much less. The difference between the epidemics and the fraction of population got infected is due to the household size different distribution. Poland did a little bit worse, especially we acted in the second and the third wave with delay, but then the restrictions were actually also pretty strong. And so we could have done better, but if we would done just as much as the European mean, we would have won a little bit, but it would not explain why the main difference is still coming from the household size. So it's not just the lack of restrictions we had, which is a little bit less good, but than the mean, but the structural effect has an impact here. And I think some countries like Bulgaria, they don't have so large household, but they are the NPEs, the things they do against the epidemic. It's just one big mess. And you see it also with a vaccination rate of 20%. You cannot say that the country really encouraged their people to take vaccinations. There, nobody cared anything. And it's really the big outlier here. Islands in general, like Ireland, but also some other islands like Malta, they have an island lake and they have a much easier situation here. I think this is an interesting thing. I want just to sketch a little bit the surface of this. And here I think mathematical theory together with data and your imagination, how epidemics going, can really reveal quite a lot of interesting things. So vaccination reduces household, we can also put it in, but let me close with some historical remarks. Looking back on the epidemics, on the Spanish flu. So this is effect of social distancing, 1900, Philadelphia and St. Louis. And what is interesting here, both towns put social distancing and forced social distancing at a certain moment. But St. Louis did it immediately after the first case detection was happening. So it was on 5th of October, 2 days later they acted. Philadelphia detected the first case 17th of December and put restrictions in, same restrictions as in St. Louis, 3rd of October. So it's the delay here which really let the things then go up, and then it's hard to stop the things. And I think this is an important thing. Even if we have very strong restrictions, you also have to put it timely to avoid coming up with a high wave. And I think this message should be clear also now for the Omicron. As earlier do a little bit, as more you have the chance that things will not go up so badly to the top. Now, mask wearing was an issue also then, and you see this I would like to have also at our workplaces. There were the radical people which claimed everybody which doesn't wear a mask should go to jail, and the anti-mask meetings also took place at that time. Nothing new under the sun. And I think I would like to add with, I had still one slide here, which I think I would like to show you because it's important. Yes, and it's maybe opening also for the discussion. Problems related to policy advice. Franek and me, we both participate here also in, well, in a certain form of policy device, I would say, by having meetings with the ministry. And I have somehow made a few points here, which I think are problematic. So sometimes we see fundamental lack of basic epidemiological understanding in decision makers. And there is sometimes wrong request, and the wrong request results also in the wrong decisions. And there is a lot of wishful thinking. So sometimes we are different, this time is different. Usually it turns out we are not different, and this time is not really different, right? So when Italy had its big first wave, all the Western countries say Italy is different. They eat spaghettis, they must be also behave differently in the epidemics. And it will not happen in our country. And a few weeks later, it happened exactly the same way, right? So this is sometimes a kind of wishful thinking. And then you delay the decision till the last moment, as I showed with Philadelphia and what was Chicago. There is, if you have the risk prevention strategy, you have a tendency in policy making that you have a selective bias to rely more on optimistic scenarios than on the pessimistic one. But for risk prevention, you should do the opposite. Experts, including myself, we are sometimes a little bit overly confident, right? We had also to pay lessons for that, things don't turn out even with the best mathematical model as they really are. And we have lack of good data on many aspects, especially at the moment, also medical aspects. We have sometimes non-transparent decision structures. And politicians and decision makers are also impacted by their belief about the public opinion. In Poland, for instance, is a myth that Poland would not accept stronger restrictions, right? This is just a myth, I think. Social scientists say that this is not true. Many people would actually wish a little bit more restrictions to have a lesser aggressive epidemic as we had. I think this is for the moment everything I wanted to say, and you can find off our MOCOS page a lot of people which have been active, are active, and are in part active here. We have also some references, and I think I have anyway taken more time than I should, and thank you very much.